Good morning. So this is the last topic on the Markov chains. Just so you know, after this there will be one last topic covered on 3 sections, a little bit shorter ones, at least the first one. And the last one I think it's also kind of short, which is basically about game theory, another interesting topic where we make good use of matrices. This last topic on a Markov chain, namely the so-called absorbing Markov chains. And we also kind of alluded already what an absorbing state is in the previous section. But this topic is, again, in my opinion, a very interesting topic, especially if you think in terms of, again, long-term behavior of a random experiment, which is repeated an unlimited number of times. So what is the long outcome of long-term outcome when you repeat the experiment? This in the context of the so-called absorbing Markov chain, which means it contains one or more states that have the property that once you reach that state, you will never leave it. So let's actually, describe what an absorbing state is in an informal way, in meaning that just using regular words. So an absorbing state means that once the Markov chain process reaches that state, it will never leave it on further trials of the experiment. So I hope it's clear what that means, right? So in general, when you reach a state, you have a probability of going to a different state, right? So remember in the notation of the transition matrix, so if P is a transition matrix of the Markov chain, the entry Pij represents the probability of moving from state I to state J. So with that remark, notice that the state, and that's the formal definition here, the state I is absorbing if the transition from that state to itself, so Pii, is equal to 1. So the probability of transitioning from that state to itself is equal to 1. So if you remember how we illustrated, this process with various states using some sort of diagrams, right? So you have a probability of, let's say, moving from I to J. But then if J is absorbing, that means the probability of moving from J to itself will be 1, right? So if you were to sketch the diagram of an absorbing absorbing Markov chain, it will look like that, right? With probability 1 to go to itself, basically, right? Because to say that it doesn't leave that state means that there's 0 probability of moving to any other state besides itself. So keep that in mind when you look at the example and to see how you can recognize immediately whether the Markov chain is absorbing or not. And make sure you don't confuse with the fact that any Markov chain which has an entry equal to 1 is absorbing, because that's not the case. It has to be 1 on that element in the same row and column. So in the previous lecture, actually, we had an example with either driving or walking. So if I remember correctly, it was like, if you drive today, you're equally likely to drive tomorrow or walk tomorrow. If you walk today, then you drive tomorrow for sure, and you're not going to walk tomorrow. So notice this is not absorbing. So there is no absorbing state in this Markov chain, because this entry equal to 1 is P21, right? So there is a probability transition equal to 1 from state 2 to 1, but not to itself. On the other hand, if you say also in that example, if we had First row the same, but the second row we said, okay, if we walk today, for sure we're not going to drive tomorrow, but if we walk today, for sure we're going to walk tomorrow. So that means you're going to walk forever after one observation, essentially, right? I mean, if you're in the walking state. If you're in driving state, again, you may drive or walk next day, but once you reach the walking state, if you walk today, for sure you're going to walk tomorrow, and then the day after tomorrow, and so on and so forth. So notice in this case, P22 equals 1, so that means the state 2 is absorbing. This is kind of an artificial example because, you know, why would you walk forever, right? If you walk today. But there are many other examples where it's very obvious that realistically speaking, that state should be absorbing. So let's start with a realistic example, which all of you should recognize. If you are a student at a four-year college, bearing some exceptions, basically you fit into one of the 6 categories, essentially, depending on your level, your year in college, and whether you actually graduated or maybe for one reason or another you dropped out. So for a typical, let's write it like that. So for a typical student, we have 6 states with respect to the level, right, of the year in in college. So you're gonna have freshman, so 6 states. You could be freshman. Let's label that with F. You could be what's the next level? Sophomore. Label that with S. Junior, which is the 3rd year, we're going to label that with J. Senior, and then the states which will be absorbing actually the dropped from college, let's label that with D, and graduated, label that with G. So let's write down the transition probabilities from one state to another, and then we're going to write the transition matrix in a very specific way, which is important for later when we actually learn a couple of interesting tools on how we analyze these absorbing Markov chains. In particular, what we're going to do, we're going to actually write these states first in the transition matrix P, right? The absorbing states. But let's write down the probabilities first. So let's say if you are freshman, there's a 0.6 probability of moving to the sophomore stage. Actually, I need to use a different, because I have the same letter, senior or, so let's say sophomore, S-O-F-P-H, and this is senior. I can't use the same letter, S. So you move to sophomore with probability 0.6, which means, and the remaining possibility, let's say, is to drop with 0.4. So if you're a freshman this year, you have a probability, let's say, of 0.6 to be a sophomore next year, or there's a probability 0.4 to drop out. Again, forget about the realistic value of these. Maybe it's too big, actually, you know, to drop out, but don't think about whether these probabilities are realistic. So this is just an example. And so let's say that the probability of dropping decreases as you move along in the process. So if you are sophomore this year, let's say there's a probability of 0.7 to move up to the junior position. We're going to actually use words from now on just to make it less confusing. And then 0.3 to drop. Then if you are junior, let's say there's a probability of 0.8 to be senior next year. So each trial is basically moving from one year to another. And then 0.2, obviously, the remaining up to 1 to drop. And then finally, if you're senior this year, let's say there's a probability of 0.9 to graduate, which means there's a probability of 0.1 to drop. When we write the transition matrix, let's this time label the rows and the columns and make sure, and this is an important remark with the absorbing Markov chains. So always write the absorbing states first in the transition matrix. Because that will give a structure which is recognizable from any Markov chain with absorbing states, and the main tool we're going to learn about it can be used easily. So always the absorbing states first. And notice in this case, obviously the absorbing states will be to graduate and to drop. Again, I mean, you can change this a little bit, because if you drop this year, maybe you can re-enroll next year. But let's suppose that's not going to happen, right? So once you graduate, of course, that's absorbing. You're not going to go back to redo the college, right? So you remain graduated from college. And let's suppose that dropping means in this context, giving up on the college education completely. So that means both of them are absorbing. Once you reach that stage, then you remain there. Okay, so how does the transition matrix look like in this case? So we're gonna, like I said, we're gonna label this with the name of each state: dropped, graduate, freshman, sophomore, junior, senior, and the same thing for the columns. So you could be dropped, graduate, freshman, sophomore, junior, and then senior. Okay, let's see how it looks like. I think I have a little bit too less. I didn't put enough space there, but hopefully it's gonna look okay. I wanted to put letters for each state, but in the end, I think I changed my mind just to see clearly the label of the the name of each state. Later on, of course, you could use numbers so that you have an easier time when you write down the matrix here. So you can use numbers, just make sure you know what each state represents. So let's fill in the transition probabilities, right? So again, remember the meaning of each row is that if you are in this state given by the label of the row, then each entry in that row represents the probability of moving to the state above. Okay, so from drop to drop, that's the probability 1, which is again the hallmark of the or the sign that that's going to be an absorbing state. So once you drop, you remain dropped out. So of course, transition from drop to graduate, freshman, sophomore, junior, senior, all of these are 0. Furthermore, from graduate to graduate, probability 1, that's absorbing. All other transitions should be 0. And now pay attention to put all the other transitions in the correct position. So now we're going to look at the probabilities given in the beginning, right? So we have from freshman to drop, there's a probability of 0.4. From freshman to graduate, that's the probability 0. From freshman to freshman, it's 0. Or from freshman, you can advance to sophomore with probability 0.6. And again, 0 all other probabilities. So take some time when you write the transition matrices, because it's very easy to misplace these probabilities. So they have to be in the correct row and column. From sophomore, we can move to junior with probability 0.7. So from sophomore, you go to junior with probability 0.7, or from sophomore you can drop with probability 0.3. And again, all other transitions should be 0. What happens from junior? Well, from junior we can advance to senior with probability 0.8. Or from junior you can drop out with probability 0.2. And again, all others are 0. And then finally, from senior, you can graduate with probability 0.9, or you can drop out with probability 0.1, and then all other probabilities are 0. So I'm going to actually rewrite this matrix in this corner to make it clear. So we have P11 equals 1, P22 equals 1, because P2 state 2 is for the graduate. And so, because I want you to notice that this matrix has a very regular structure, so to speak. So you have 1, 0, and then followed by 4 more zeros. 0, 1, and then zeros again. And then going to be 0.4, 0, 0.6, 0, 0, 0.3, 0, 0, another 0.7 and 0, 0.2, 0.8 over here, and then 0.1, 0.9, 0, 0, 0, 0. So I think I'm going to write it on the next page as well. So notice that if you arrange these absorbing states in this fashion, you will always have the identity matrix in this corner. Identity matrix in the left corner. Because those are the absorbing states, right? Which means those are the states in which the entries on the same row and column, P11, P22, are equal to 1, and then it's 0 elsewhere. So this corner here, depending on how many absorbing states you have, and in this case we have 2 absorbing states and 4 non-absorbing states, then so depending on the number of absorbing states, you have an identity matrix which can be 2 by 2, 3 by 3, and so on and so forth. And then on the right corner here, you have a matrix that is always equal to 0, a matrix with the number of rows given by the by the absorbing states, and the number of columns by the non-absorbing states. And then 2 sub-matrices here on the left down corner and the right corner over here. These matrices will have actually an important use, as you will see on the next page. But each absorbing state, each transition matrix of an absorbing Markov chain will have this type of structures. And we're going to write it in a more general way on the next page to illustrate how that works. So stay tuned for the next page. Okay, so let's continue. I rewrote the matrix here to have it in front of us. And then now let's write down in a general way how the transition matrix of an absorbing Markov chain looks like in general, right? So let's write it as a subtitle here, the structure of the transition matrix of an absorbing Markov chain. And let's say with R absorbing states and S non-absorbing states. So for the record here, in the example we had before, the R is equal to 2 and S equals 4, right? So drop, graduate were the 2 absorbing states, and freshman, sophomore, senior, junior, right, were the non-absorbing ones. If you put these, like I said, the absorbing states first, the matrix P, the transition matrix P, always looks like this. In the corner, in the left up corner, you're gonna have the identity matrix with R rows and R columns. Here you're gonna have a 0 matrix with R rows and S columns. in the down left corner, you're going to have another matrix which is going to be denoted by S. So make sure you write it just like that as in the formula sheet, which will be with S rows and R columns. And here a matrix denoted by Q, which will be with S row, S columns. So just for the record, IRR stands for 1, 1, 1, and zeros elsewhere, right? So the identity matrix with R rows, R columns. By this big zero, RS, I just mean basically the matrix with zeros everywhere, right? I mean, but again, that's not a square matrix, right? So the number of rows and columns of that zero matrix is just depending on the value of R and S. So this is always the case for any Markov chain with absorbing states. Again, if you arrange it in that form. So to illustrate here in this example, the IRR is actually I2 too, if you want. And I think it's, sorry about that, I think it's just IR, right? The typical notation for the, because I want to indicate the number of rows and columns, right? So just a single R, IR, IN, that's the notation of the identity matrix. So I2, in this case, in this corner, is going to be 1, 0, 0, 1. The zero matrix, which will be with, in this case, 2 rows and 4 columns, is going to be just, as the name implies, the matrix with entry zeros and 2 rows and 4 columns. We're not going to use the zero matrix. This is just as a quick check that your arrangement is correct. Then the matrix named S, big S in my case, will be 0.40, 0.30, 0.20, 0.1, 0.9. And again, pay attention to the number of rows and columns, right? So the number of rows is given by the number of non-absorbing states, 4 in my case, and the number of columns by the number of absorbing states. And finally, the matrix denoted by Q, that's going to be a 4 by 4 matrix. It's always a square matrix given by the number of non-absorbing states. So this will be a 4 by 4. All right, so you may wonder why do we bother with this? Well, because there are 2 matrices that we can compute based on S and Q, which will give us important information about the long-term behavior of this Markov chain. For example, because let me give you here a little motivation of why we bother with this. We may ask questions like, if so let's say we ask, what is the chance, or what is the probability that a freshman eventually graduates or eventually drops? Because notice that the probability of going into, or the chance of going from freshman to graduate depends on many other possible things that can happen with each trial, right? Because as you move from freshman to sophomore, then to junior and so on, there's always a chance of dropping out. So then it's of interest, for example, for administration of the college to know, an entering freshman, there's always a chance that he or she will drop out. What is the chance that he or she will eventually drop out? What is the chance that he or she will eventually graduate, so that we know that we have our goal reached in terms of graduation rate and so on? So this is not about the question of what happens from one transition to another, but what happens in the long run in terms of, does that state that the student started it with, does that state results in graduate or dropout? So eventually, if you have an absorbing chain, a Markov chain, the state will be one of the absorbing states eventually, but the question is which one is which, right? And another question is, after how many observations that happens. So we can answer these questions with 2 matrices derived from these matrices S and Q. We're going to provide this without proof, but we're going to illustrate with an example. So there are two matrices to compute based on S and Q. The first one, called T, which is called the fundamental matrix of the absorbing Markov chain. So this fundamental matrix, denoted by T, is the inverse of the matrix obtained from subtracting the matrix Q from the identity matrix with S row and S columns. And then another matrix doesn't have any name, but we're going to call it, we're not going to call it anything, it's just T times S. So once you actually come up with the fundamental matrix, you can also compute the matrix from multiplying T with the matrix S, which will give us another important piece of information related to the long-term behavior. So we're going to illustrate with examples on the next page immediately. But just for the record, in this case, IS, like I said, IS is going to be, because we have four non-absorbing states. So the identity with 4 rows and 4 columns will be this matrix. And then Q is this one here. So then when you take the inverse, you first subtract from the identity matrix the matrix Q. We're going to do this with Maple later because this is too tedious to do by hand. We're going to do by hand as a shorter example. And you take the inverse of this. I hope it's clear enough here. So you subtract IS minus Q, take the inverse, and that's the fundamental matrix. So how do you use the fundamental matrix? Or in other words, what does the fundamental matrix tells you? Well, the entries, so the meaning of the entries of T is the following. The sum of the entries on each row is the expected number of trials or observations before absorption for each non-absorbing state. It's going to be clearer once we get an example, but we have to state here the meaning. So once you compute this matrix, you look at each row. Each row represents a non-absorbing state. So if you add the entries, so the sum of the entries on that row, it'll give you an estimate of how many observations do you need to run until that state ends up in an absorbing state. Notice it doesn't tell you which one, right? Because it can be, in this example of ours, it can be graduate or dropped, but it will tell you the number of times until you will expect that absorption to happen. So to put it clearer, let's say that if suppose the T matrix has these entries in row I, right? So TI1, TI2, TIS, right? So that means TI1 plus TI2 plus ... TIS will give you the number of trials before absorption from state I. Okay, so from state I, number of trials until absorption. Finally, the product between T times S, again, if you do this product correctly, this will be a, if you look carefully, this will be an R by S matrix. It will have the number of rows given by the, not R by S, I'm sorry, S by R matrix. The number of rows will be again the non-absorbing states, and the number of columns will be the absorbing states. So each entry of this matrix is the probability of starting so each entry, let's call it each entry ij, right? Row I, column j, is the probability of starting in non-absorbing state I and being absorbed in state j eventually. Okay, so the probability that you start in a non-absorbing state and you eventually are absorbed in state j. So like I said, in the next page, we're going to do an example by hand with a simpler case, and then we're going to run a maple case with this very example, because this is not feasible to do by hand over here. So let's stay tuned for the next page. All right, so let's look at an example, which is a famous example called the gambler's ruin problem. Again, another example useful in real life if you plan to play a game of luck repeatedly. And then you, of course, as it's advisable, you make yourself some stopping criteria. One of them is involuntary, right? For example, you run out of money, but also you may want to stop when you are ahead. Like, for example, if you win a certain amount of money, you decide to leave the table. So there are variations of this problem, but one of the easiest ones in terms of the math involved, so we can actually go through it, involves essentially 4 states. So let's read it together. Take a moment to write it down and then read it with me. So a person repeatedly bets $1 each day. Now, if the person wins, he wins $1. So that means you keep the bet that you put on the table and you receive another $1, meaning that you're going to have $2 after that. The person decides to stop playing if he reaches $3 or runs out of money. So pay attention to these stopping criteria, because these states, these stopping criterions will give you the absorbing states, right? So you're going to stop the game when you reach $3 or when you run out of money. That means $0. Let's say the probability of winning is 0.4 over here, and obviously the losing is the complement, 0.6. So then you can have possible questions like, what's the probability of eventually accumulating $3 if the person starts with $1? What about if he starts with $2? And so on. By the way, intuitively, you should realize that the probability of getting to $3 is a little bit bigger if you start with $2, because obviously you can afford to lose more times, right, than when you start with $1. If you start with $1 and lose on the first trial, then you're done. So now let's focus on arranging this transition matrix as given here in this corner. And the first thing to do is to identify the absorbing states. So I hope it's clear that in this case, 0, 3 are absorbing states. And by the way, I should have said what are the possible states before we even talk about that. So because each game gives you $1 of winning or losing $1, there are 4 possible states. You go broke, you start in the first tile, you start with $1, so you could have $1. You could win another $1, so you could have 2. You could win another $1, so you could have 3. But once you have 3, you're going to stop. Excuse me. So you have in total 4 possible states. Okay. Of which 0 and 3 are absorbing states, because obviously you cannot play anymore if you don't have any money, or you plan to leave the table if you accumulate $3. So when you write the transition matrix, remember to always place the absorbing states first. So just like before, let's label the rows and columns with the absorbing states. And let's focus now on placing the probabilities on each row and column. Okay, So 0 is an absorbing state. Once you have no money, you're going to be left with no money. So 0 to 0 is 1. All the other probabilities are 0, 0, 0. If you have $3, you decide to leave the table. So the transition from 3 to 3 is going to be 1, 0 elsewhere. Then if you have $1, there are two possibilities. Either you win $1 and you get to $2 with probability 0.4. So the transition from state 1 to state 2 is going to be 0.4. In the way I arrange this matrix, that's going to be third row and the fourth column. Or you're going to lose the dollar you have and will give, you'll remain with $0 with probability 0.6. And the other ones are 0, 0. So from $1 you can get to $2 or to $0. From $2 you can get to $3 with probability 0.4. Or you can get to $1 if you lose $1 with probability 0.6. Again, pay close attention to the position of these transition probabilities to be in the right column and row. So when everything is said and done, your transition matrix is going to be 1, 0, 0, 0, 0, 1, 0, 0, 0.6, 0, 0.4, 0, 0.4, 0.6, and 0. And obviously it will have the structure that we talked about in the previous page. So notice that in this case, what we call matrix S, corresponding to the non-absorbing states, $1 and $2, will be 0.6, 0, 0, 0.4, and the matrix Q is 0, 0.4, 0.6, and 0. In this case, the number of non-absorbing states is the same as the number of absorbing states. That's why these are square matrices. Q doesn't have to be a square matrix. No, excuse me, the other way around. S doesn't have to be a square matrix. So the fundamental matrix comes from taking the inverse of the identity matrix SS. So in this case, again, R is 2, S is 2. The number of R is 2, S is equal to 2. The number of non-absorbing or absorbing states. So T is the identity with S rows and S columns, 1, 0, 0, 1. And minus Q, which is 0, 0.4, 0.6, and 0. So we have to take the inverse of this matrix. And this might be a good time to review how to take the inverse. It's, remember, an application of Gaussian elimination. Just make sure you do the difference first of these two matrices before you implement the algorithm of finding the inverse. So in this case, 1 minus 0 is 1. 0 minus 0.4, that's minus 0.4. We subtract term by term, right? So 0 minus 0.6 is minus 0.6. And then 1 minus 0 is 1. So we have to take the inverse of this matrix. Okay, how do we take the inverse? Well, remember from that section, we take the augmented matrix. We augment the matrix T with the identity matrix, and we must produce the reduced, so must get the reduced row echelon form, and the inverse will be read on the right half of this augmented matrix. So how do I find the inverse? Well, the row reduced echelon form. So we need to have 1 on the first position and 0 before. We already have a 1. So we're going to do row 1 times 0.6 plus row 2. You're going to have to use the calculator to follow up on this. So 0.6 times 1 minus 0.6 is going to be 0. The next entry, which is minus 0.4 times 0.6 plus 1, that's going to be 0.76. Then it's going to be 0.6. And then it's going to be 1. Again, slow down and follow up with the calculator if you need to. The next thing is to make 1 on the second row. So we're going to divide row 2 by 0.76, I'm sorry. So that's going to be 1 minus 0 0.41001. 0.6 over 0.76 will be 0.789. And 1 over 0.76 will be 1. Man, I don't have room here. I'm going to write it here on the last second from the beginning. 0, 1, 0.789, and the last entry here will be 1.315. And then finally, to produce the row echelon form, reduced row echelon form, we're going to have to make a 0 above the second leading 1. So that's row 2 times 0.4 plus row 1. And if you follow up with the calculator, the entries now should be 1, 0, 1.3156, 0.526. You can actually leave only 2 decimals if you want. Then 0.789, 1.315. Please make sure you run out these computations with the calculator just to see where it comes from. But anyway, this is going to be the inverse of this matrix. So that means the fundamental matrix is 1.3156, 0.526, 0.789, 1.315. And then let's just do t times s just to have it here. So and then we're going to talk about the meaning of the these entries. So actually, let's talk about right now. Remember, the rows of t represent the non-absorbing states 1 and 2. Adding the rows on each, so adding the entries on each row tells you how many times you would expect to play the game until absorption. So for example, for the $1, if I add the entries on the first row, that's going to be approximately equal to 1.8. So that means I would expect to play 2 times before absorption. And if you look carefully, if you start with $2, it's a little bit bigger than that. So if I start with $2, it's like 2.0, right? A little bit more, right? If you have $2. So on average, remember, this is basically how many times you play on average until you have an absorbing state happening. But notice this doesn't tell you what will happen exactly. Basically, going broke or winning $3. It tells you how many times you would expect to play until one of these outcomes will happen. So that's the meaning of entries of t. When you compute t times s, so you multiply the fundamental matrix you just obtained, 1.3156, 0.526, 0.789, 1.315 with the matrix S, which in my case is 0.60, 0.4. Do this computation on your own. This will end up being 0.789, 0.21, 0.47, 0.526. These are the probabilities of being absorbed in a very specific state, right? So again, if we label the states here, each row represents a non-absorbing state. Each column represents the absorbing state, $0, $3 in this case. So now to answer the question, if I look at entry 1, 3, right? I mean, like row 1, column 2, 0.21 is the answer in the first question. If I start with $1, what's the probability of ending with $3? So start $1 and with $3. And notice that if the complement probability is 0.789, that's the probability of starting with $1 and ending with $0, going broke, basically. And as expected, if you start with $2, it's a slightly bigger probability of winning $3. So if I start with $2, That's the probability of ending with $3. And finally, if I start with $2, so 0.47, this entry in the lower corner is the probability if I start with $2 and end broke with $0. So you kind of expected, right? The probability of winning was lower than the probability of losing. So there was a higher chance of losing, which is the reason why the worst outcome is if I start with $1. That gives me the biggest probability of going broke. And that's the reason why the lowest possible probability is starting with just $1 and ending with $3. So I hope that's clear. Make sure you watch also the Maple example, because these computations they're not that easy to do on paper. So I'm going to show you how the matrix looks like for the previous example with the graduation and dropping out. So I'm going to do that using Maple. So make sure you understand the interpretation of the results. And with that, that's it for today.